let's go straight to the Zoom whiteboard. And where we left off last time was the cyclic block code theorem. And so this is the idea we are now talking about. So we've made this mapping. So let me set the stage again for you. We have data words and code words. Those data words are just sequences of bits. We'll call them k bits long, and the code words are sequences of bits. We'll call them n bits long. But you can either think about them as sequences of ones and zeros, or you can think about them as polynomials whose coefficients are either 1 or 0. So we're going to associate the data word in a k-dimensional vector space with a k-1 degree polynomial. And that mapping is 1 to 1. Every string of bits that are k long represents a single and unique polynomial that is of degree k-1. So that allows us to get a little bit of extra, like you might be thinking, why even bring polynomials into the discussion? And the main reason is because of their facility with multiplying polynomials, in particular dividing polynomials, and then talking about remainders instead of modular arithmetic. So those two will go hand in hand, remainders and mod whatever arithmetic. It will allow us to go beyond mod 2 eventually. But for starters, we'll stay in Galois fields. Our coefficients are going to be ones and zeros, and every sequence of bits can be thought of as a polynomial where those bits represent the coefficients on x in descending powers. Okay, so a cyclic code, to refresh your memory, is any mapping, is any encoding in which any code word, if you shift it by any amount, either left or right, you will get another valid code word. So it's a way to take the space of all possible mappings from k space to n space and condense it into maybe something that's a little bit easier for your decoder, for your receiver to analyze. And so if all of your code words are cyclic shifts of each other or linear combinations of those cyclic shifts, then it reduces the computational complexity of the receiver's architecture. Okay. So in order to generate a cyclic code, one can have a generator matrix. I called it G of X last time. We'll also see that you can go back and think about cyclic codes in terms of linear algebra. And so there's nothing stopping you from building a generator matrix for a cyclic code. But I think it's a little bit easier to see the cyclicity with the polynomials. And so the big theorem at the end of last class was, if I hand you a polynomial that happens to be degree n minus k, and it is an exact factor of the polynomial x to the n plus 1, then that polynomial that I just handed to you is a generator polynomial for an nk cyclic code. So it really, the only two requirements of a generator polynomial for a cyclic code are these two in the conditions of this theorem. It has to be the correct degree, and it has to be a factor of x to the n plus 1. So let's, for a quick aside, let's talk about this line. This means, this is equivalent to x of n plus 1 over g of x is a quotient polynomial and no remainder. Okay, so this is what it means to be a factor. This is kind of natural when you're talking about integers, but as we'll see, things we can say about integers we'll often be able to say about polynomials. So you can either think of it this way, or even that is equivalent to x to the n plus 1, which is itself a polynomial, equals a quotient polynomial, I'll call q of x, times g of x, with no remainder again. Okay, so all I'm saying is that there exists a q of x that when you multiply by g of x, you get x to the n plus 1. You don't need to add any extra bits over here. Okay, and this is actually a good segue to talk a little bit about terminology. When I have these four players, so 1, 2, 3, 4. Well, we've talked about how player number 3 is called the quotient. It's the result of the division. Player number 4 is called the remainder. And then players number 1 and 2, let's see, I can never remember which one is which. You're dividing by g of x, so that's going to be your divisor. And the thing on top, which we all call the numerator, is technically called the dividend, the thing being divided. Okay. And one more factoid. Sorry, this isn't the proof that I promised you, but it is convenient to talk about it now. One more fact is that the degree of the remainder is always less than, no, strictly less than the degree of the divisor. Okay. So, and this is also how you know to stop your long division, is when you get a remainder whose degree is actually less than the degree of your divisor. That just means that you can stop doing your long division. So it's a termination condition on the algorithm. Okay, so let's go back and talk about how one might prove this claim, that there are really only 2 requirements on a cyclic code generator. So I think the way to think about this is, let's pick an arbitrary data word. We'll call it D, and we'll represent it as a string of bits. We'll call those bits D1, D2, up to D sub k. So it's an element of the k space. And that means that this data word can be represented as a polynomial as what? D sub 1 times x to the k minus 1, D sub 2, x to the k minus 2, and on down the line until we get D sub k times x to the 0. Well, if this is how we represent d of x, then to represent d times g of x, well, one way to think about that is just distributing g of x on the entire right-hand side. So this is d1 x to the k minus 1 g of x plus d2 x to the k minus 2 g of x plus on and on until we get d sub k g of x. And so what I'd like to do is actually keep track of the degree of all of these terms. So let's check the degrees of each of these terms. Well, by assumption, g of x has degree n minus k. So dk times g of x is going to have degree n minus k. N minus k, and if I multiply g of x by x to the k minus 2, if you multiply polynomials, you add their degrees. So let's add that to k minus 2. So I think this is, the k's will drop, and so this is degree n minus 2. And the same pattern will hold, and this will be degree n minus 1. And help me out, if I add polynomials of varying degrees, well, first off, is that legal? And second off, what will the degree of the resulting polynomial, well, I guess I gave away the answer to the first question. So can you rationalize that the sum of 2 polynomials of different degrees is a legitimate operation? This might be too obvious, like, to actually talk about.
Yes, it's possible.
Every polynomial is the sum of polynomials of varying degrees, right?
Yeah. So I didn't know if we had to do any more simplification.
No. Sorry, that was literally too easy. How about the second question? If I add polynomials of varying degrees, what is the degree of the resulting sum polynomial?
The highest degree.
The largest degree.
Good. Yeah. The max of all the above. So the max of all these orange things is n minus 1. Okay, so the resulting d of x times g of x has degree n minus 1, which is good. This is good because our code word needs to be dimension n, so it will be represented by a polynomial of degree n minus 1. Okay, so this means that dx gx lives in the same space as our c of x. Okay, so let's give this result a name. So define c of x as this thing we just did out, d of x times g of x. And it will be a degree, polynomial degree n minus 1. So let's give it a general form. It'll be c1 times x of n minus 1 plus c2 x n minus 2, and on till down to cn x to the 0. Okay, so let's multiply both sides by x. So if I go x times c of x, then I get c1 times x to the n. Everything gets bumped up by 1 power. And what else can I do? I can add c1 to both sides. No, I'll add and subtract c1. So I'm going to add c1 over here, and I'm going to subtract c1 over there. So I haven't changed the right-hand side at all. But what this trick allows me to do is factor a c1 out of the first two terms here. So that gives me xn plus 1. And then it gives me c2 x to the n minus 1 plus dot 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 down to cnx plus c1. Now, who can tell me why this negative sign turned into this positive sign?
Does that
Any
have to do with? Sorry, go ahead.
I was going to say the answer isn't that I made a mistake. So if you thought it was a trick question.
Does that have to do with the mod 2 that we're working with?
Precisely, because all of the coefficients are zeros and ones or binary, and we defined our addition to be mod 2, then if I have a number minus 1, that's the same as that number plus 1. And if I have a number minus 0 versus plus 0, I haven't changed it at all. So I can change the sign, SIGN, with impunity because we're doing mod 2 arithmetic. Very good.
But why do we care? Why don't we just leave it as minus then? Like, why are we switching it to positive?
I think it'll be easier to see the very next thing I'm going to say if I've written it as positive. But you're right. They're equivalent, so it actually shouldn't matter. What I'm about to say is this thing is vaguely familiar. It would be more familiar if we did this during last lecture. But what I have underlined here is the permutation or cyclic shift on our original code. So this is C shifted by 1. Okay, so far so good. Now what we need to do is show that this C1 is also the target of a different data word, right? Because if we can do that, then we will know that the code encoding is a cyclic encoding, because it means that if C of x is a code word, then C1 of x is a code word. And we can wash, rinse, repeat to say if C1 of x is a code word, then C2 of x will be a code word. So the goal now is we want to show that there exists some dx hat such that d hat of x times g of x equals c1 of x, right? If we could do that, then we would know that the code was cyclic. So when you're working through these proofs, and there's part of the theorem that you haven't used yet, i.e. that part, it's probably a good idea to use every part of the theorem. So to show this last part, we're going to use this factor business. Okay. So if I write g of x as a factor of xn plus 1, then I know, we know this from by assumption, that x to the n plus 1 equals a quotient times g of x. That was assumed a feature of g of x. Which means that we can take this very last line that we have, so take our expression for x times c of x, and replace c of x with d times g. And we just showed that that equals to c1 factored out of x to the n plus 1 plus this cyclically permuted code word. But we now can write x to the n plus 1 as q of x times g of x. And if I move this term, this first term, to the left-hand side and factor, I get x times d of x minus c1 q of x times g of x equals c1 of x. Okay, so we've shown that g of x takes something and maps it to a code word. Is that thing a valid data word? Can we just slap a d hat on this big parentheses and call it a day? Turns out the answer is yes, but I think it's a little disconcerting, because normally g of x takes k minus 1 degree polynomials and maps them to n minus 1 degree polynomials, right? That's what a generator polynomial does. But what is the degree of this polynomial? So we'll go back to the color for degrees. If d of x is k minus 1 degree, then x times d of x is actually degree k. Which means that if I'm taking the sum or difference here, then I'm going to get the max of two things, but the max has to be at least as big as the smallest. So there's a flaw in our logic. And the flaw is the sum of polynomials is the max degree if there's no cancellation. So walk me through this. If I have x to the 5 plus x, and I subtract from that x to the 5 plus x squared, the degree of the result is not 5. The degree of the result is 2. And so what we were doing before, when we're talking about adding, here I'm subtracting, but if we're adding, we're subtracting because everything is mod 2. You have to be a little careful that you can get cancellation of the highest power, and then you will have a degree of no greater than the max of the 2 degrees. And that's exactly what happens here, is the kth degree, it's a kth degree term in this actually cancels the kth degree term in this, meaning the entire result will actually be k minus 1 degree, which means that this entire thing is a valid data word, which means that our generator matrix, our generator polynomial, is a cyclic generator, because it takes 2 data words and it maps them to two code words that are cyclic permutations of each other. Questions?
Yeah, I have a question. How do we assume that Q of X has a kth degree term?
Good
Or
question.
necessarily how?
So where did Q of X come from? It came from up here. And if we know that G of X has degree n minus k, and we know that the left-hand side here has to have degree n, then that tells us that Q of X is degree k.
Okay.
Yeah.
That makes sense.
Yeah. So yeah, the two things in this parentheses are both degree k, but they are such that, or we constructed them such that the things multiplying x to the k will always cancel.
Okay, that makes sense. Thank you.
Hey Clay, when you wrote in red, want to show like d of x hat, what's that symbol before d of x?
There exists.
Okay, thanks.
Yeah. Okay, so yeah, I thought this was a pretty cool little result, is that there are only two requirements that a generator polynomial generate a cyclic code. And that is that it has the right degree, okay, duh, but that also if it's a factor of this, in this weird kind of constraint that it has to be a factor of x to the n plus 1, once you've satisfied those two, then that polynomial is guaranteed to generate you a cyclic shifting code. All right. So I think just to tie back to another thing we've seen, to give you another callback to these block codes, is the following question. Can cyclic codes be systematic? So let's recall, actually you tell me, what does it mean for a code to be systematic?
Is that where the code bits are just at the very end? It's like the data bits and then it's the code bits,
Good.
and it's
Yeah,
not interspersed.
exactly. So yeah, it's just the frame check sequence is a block literally at the end of the frame. Good. So before we give away the answer, what would it mean for a cyclic code to be systematic? Or what would it mean for a polynomial representing this code to be systematic? What would the code polynomial have to look like? If I am given d of x, what would its code polynomial have to look like? Remember, if we're going to have data stuff and then check stuff. So if it helps you to think about this pictorially, here is d of x. Here is what c of x would look like if it could be systematically encoded. And what I want to do is I just want to pick up d of x and I want to move it kind of up or down to the left here. I want to increase its power and then add on some extra frame check bits over here. Now I can move d of x up if I multiply it by x. Right? If I take d of x and multiply x, then I've shifted every power up by 1, so you can think about it as moving it to the left. If I want to move it up, I'd have to move it up by x to the n minus k times d of x. And then I would add the frame check polynomial at the end. Okay. So this would be f of x, the frame check polynomial, and then this would be x to the n minus k times d of x. Okay. By multiplying d of x by x to the n minus k, I have kind of opened up these lower order terms that we can add a lower order polynomial into and not change the degree of the overall polynomial. So if the answer is yes, then we'd have to be able to write the code word in this form. Anyone not follow that? Okay. So what I want to do is ensure that we can do this in a cyclic manner. So for my next trick, I want to define the quantity rho of x. Rho is going to be kind of like r, kind of like remainder. Rho of x is going to be defined as the remainder when I take x to the n minus k, multiply by d of x, and then divide by the generator. Okay, so we're going to have a lot of these operations like rem. So do a division, and then I don't care about the quotient. All I care about is the remainder. So that's what I'm saying here. So if we take this definition, this means, so this implies that x to the n minus k times d of x can be written as, well, divide that by g of x, can be written as a quotient polynomial. And I'm sorry that my q's and my g's look so similar. That is my fault, not yours. Q of x plus rho of x over g of x, right? This is what it means to be a remainder. And what can we do now? Well, we can add rho of x over g of x to both sides and maintain equality. But here is the question. If I add two things, mod 2, and those two things are the same, what do I have to end up with? Good. This is mod 2 addition is all about XORing. So if I XOR something with itself, that can't be anything but 0. It has to be false. So that leaves us with x to the n minus k times d of x plus rho of x all over g of x equals q of x. Move the g of x over. And I think what we have just shown is that q of x lives in the data word space, and it gets mapped to x to the n minus k times d of x. It gets mapped to the form that we want, where the frame check sequence, or frame check polynomial in this case, f of x is equal to rho of x, which you can get by finding the remainder of this thing. So let me walk you through that a little bit more slowly. If you hand me a data word, I'm going to call that now d of x. And I have in my back pocket a generator polynomial. So if I take your data word, multiply it, or bump all its powers up equivalently up to by n minus k powers, and then divide that by g of x, and then take the remainder of that division, what I get out of that is going to be the frame check sequence, which tells me that the code word for this systematic code is going to be x to the n minus k times your data polynomial plus the frame check polynomial that we just got. So the answer is yes, and this is the manner in which you would encode that. So let's see an example, if unless there are questions right now. Okay, so this comes from your textbook. This is Lothian Ding example 13.4. And the idea is construct a 7-4 systematic cyclic code. And we're given a generator polynomial, just handed to us. Okay, so let's take a moment and pause and make sure we understand everything that's being handed to us. So we're supposed to construct a code. And remember, a code is another word for a mapping from a data word space to a code word space. So if we can identify how every data word gets mapped to a code word, then we've completed the assignment. That sounds kind of nasty, but until you realize that we're being told that the data word space is only 2 to the 4 elements. So we're only looking for 16 correspondences. And we're also told that the code words are going to be 7 bits long. Okay, so that's that information used. We also know that what we're going to get is a cyclic code. So if I find one code word, then I get a bunch of code words for free because I get to cyclically shift it around and get a whole bunch of other code words. So one approach would be to pick an arbitrary data word. And the textbook picked 1010. It helps if you don't pick all ones or all zeros. So pick something that's not the same bit repeated over and over again. Okay, so if this is our data word that we want to map, then let's make it a polynomial. So remember, we're doing the bits become coefficients. So this is x to the 3 plus 0 x to the 2 plus x to the 1 plus 0 x to the 0. So without all the extra stuff, that's x to the 3rd plus x. Okay, so to form this systematic code, we need to find that remainder term, that row that I was talking about. So now we got to find x to the n minus k times d of x divided by g of x. I don't care about the quotient, I care about the remainder. But it turns out that we're going to have to do the long division, so we'll get both. Doesn't really matter. So if I am dividing by g of x, then the g of x goes outside, x to the 3 plus x squared plus 1. Uh-oh, the wind is picking up. I hope. This is exciting. I got to get the lecture in. And then what is being divided is, well, we actually know n minus k, so there's actually no point in leaving it as n minus k. This is 7 minus 4, so that's x to the 3. So everything gets bumped up by 3 powers. So I end up with my dividend is x to the 6, and then I'm going to leave an extra blank there, plus x to the 4, and then a bunch of more blanks there. Okay, so again, the dividend is x cubed times d of x, and that's our d of x. Okay, all right, this is fun, long division. So I need x to the 3rd to get my x to the 3rd into x to the 6, and then I get x to the 5, and then x to the 3. I would normally subtract if we were doing grade school long division, but because subtraction is the same as addition mod 2, we can throw all the signs away and just line everything up in columns and you're good to go. So 2x to the 6s, if you XOR them, you get nothing. So I'm left with x to the 5, x to the 4, and x to the 3. Questions on that? Because I think if you're with me on this step, then we can do the rest a little bit more quickly. The trick mentally for me was just letting go of negative signs and just accepting that pluses, minuses, it's all the same. Okay, so now I need x to the 2 to get me x to the 5, and then x to the 4, and then x to the 2. Do your XOR, and you get x to the 3 plus x to the 2. Now we're in equal powers, so I've got to go once more. So now I need 1 x to the 3, x to the 2, and 1. XOR that, I get 1. So if I put the signs back in, this is my q of x, this is my row of x, and I'm ready to present to you our first code word. So this data polynomial becomes the code polynomial, which is x to the 3 times our data polynomial plus our remainder, which in this case, it happens to be this very simple polynomial, just 1. Okay, so that implies that our code word is going to be, well, I got an x to the 6, 0x to the 5s, 1x to the 4, 3, 2, 1, blast off. So data word 1010 becomes code word 1010. So that's the systematic part. There's our data word 001. Now, we are getting this from a cyclic generator polynomial, which means that other code words are hidden inside here, right? This means that 01, 00011 is also a code word. It also means that I keep going through here, 3 zeros, and then 2101. Nope, too many bits. Right, so you can keep cyclically permuting this, and because it's systematic, the bonus is this is the code word for this data word. Sorry, you can't see what I'm pointing to. This is the code word for this data word.
We actually can see your cursor, actually. So. If you
Oh,
just...
okay. So you can see where the pencil lies?
Yes. Well, I do at least. I don't know. It's everybody.
Fabulous. I can't, and I'm sitting in the same room. Okay, so this is a way to generate some of our table that we need, right? It can't be all of it, because out of this, how many possible cyclic shifts are there? Well, this is like 7, so there's going to be only going to be 7 code words by permuting it all the way around. But we need 2 to the 4, so 16 are needed. The other benefit is that all these cyclic codes that we are developing are also linear codes. So that means that sums of code words will also be code words. So for example, if I were to add these 2 vectors, then I get 1, 1, 0, 0, 1, 0, 1. And so this tells me that data word 1100 becomes code word 1100101. So this is a way for you to fill out the table, which would in general be 16 long, running from quadruple 0 up to quadruple 1. And then there would be one and only one element in the right-hand column. Okay. I mean, alternatively, you can just go through all 16 of these and do the long division, get the remainder, and that is perhaps a more trustworthy way of doing this if you don't buy this operation that I'm doing over here. It's far more labor intensive, but I think it would convince you beyond a shadow of a doubt that one, maybe you should trust me next time, and two, that we are doing something legit here.
Clay, I have a quick question.
Go for it.
So you're saying there's 7 cyclical permutes for a 7-4 system. And if you were to XOR 2 of them, you can get a code word for another's, like a different data word value.
Mm-hmm.
If you were to XOR all of them, do you get exactly 16 or do you get more than 16?
You would get repeats. You would end up with repetitions. So you would end up with 16 unique ones. But you would get, like, you could take all different manner of combinations of these 7-bit long strings, and XOR them, and you can do this until the cows come home, but you're only going to get, in the end, 16 unique code words, or
right,
words.
That makes sense, because I guess each data word has its own unique code word. So if you get the same data word, you'll get the same code word. Okay,
right.
Thanks.
What else does this mean? This also, since it's a linear code, then we're guaranteed that quadruple 0 maps to septuple 0. Because if you XOR something with itself, you get zeros, all zeros. And so by linearity and by systematicity, these guys show up here. And so you just get the all 0 check bits for all 0 data bits. All right.
Does that also apply to ones?
I think it does. Yeah, I think that same result can be written down here. That the very bottom left of the cube maps to the bottom left of the cube, where now I'm talking about hypercubes, right? 4-dimensional, 7-dimensional cubes. And then the upper right of the cube maps to the upper right of the 7-dimensional cube. There were 2 questions, and I heard only the one.
Oh, I just had a statement. I guess I see why you would use like a 1010. You want to do like and or operation or XOR operations to find more code words from your data words.
Yeah, I think this is a reasonable approach. Is do the hard work or do the long division once, and then kind of use your properties from there on out. It's kind of the same as Fourier stuff.
Okay, cool.
This is all about encoding. We haven't really talked much about decoding. So how can we get our data back using a cyclic code? So let's start with a couple of observations. So this would be decoding cyclic codes. And first off, let's denote the received bits by R of x. So this is the polynomial corresponding to received bits. And if it's a length 7 code, then there should be 7 blocks of 7 bits coming in. If it was a length 15 code, it'd be blocks of 15 coming in. If it was length 255, it would be 255th order polynomial. The first thing that we want to do is take R of x and divide it by G of x. Right? If you have an encoding decoding scheme, it makes sense that both the encoder knows G and the decoder knows G. So the first thing you should do at the receive side is take your received bits and try and divide them by G of x. Now, what's the best case scenario here? Remember how we generate these. G of x times d of x gives us the thing we're sending. So okay, maybe this is not clear. The best case scenario is no errors occur in the channel. And so R of X is the valid C of X. That means that when we do this operation, division, we should get no leftover. So best case, we get D of X and no remainder. This would mean either no errors, or, remember we can never rule this out, exactly the right errors to switch one code word into another code word. Okay, so I don't want you to think that possibility isn't possible, but it's unlikely. Okay, so let's talk about not best case. In the not best case, we're going to get a remainder when we try to divide this by g of x. So alternatively, r of x divided by g of x is going to be, well, the remainder is going to be some non-zero polynomial, which I'm going to call s of x. S of x because it's the syndrome in this case. This word syndrome is going to pop up again. Okay, so if I take the received code word and I divide it by my generator and I get something with no remainder, then I'm good. I can conclude that my division, the quotient of that division, is the data word that I want. If I do get some remainder, non-zero, then we'll call that the syndrome polynomial. And then we're in the case where our received polynomial is the true polynomial corrupted by some error polynomial. And this in conjunction, if I plug this guy into here, then I get this is the remainder of c of x plus the error polynomial divided by my generator. And this is, again, the remainder between c of x and g of x. But there will be no remainder from this operation. This, in terms of its remainder, is going to be 0. Because we constructed c by multiplying g by a polynomial, so there will be no remainder left over. So that means that the syndrome is strictly the remainder between e of x and g of x. And so this is a way to map. This is a map between the syndrome that we can get from our incoming bits to the error vector. Now, I also want to highlight before we go is that multiple error vectors can point, so call this, there are multiple possibilities of different error vectors that can give you the same syndrome. Right, just like if we had different code words, there are multiple errors that could flip them all into any given received sequence of bits. But what you want to pick for this relationship is pick out of this list the e of x with least weight. Right, the e of x with the least number of ones, because that represents the most probable event. That is, that represents the least number of bit flips, assuming a binary symmetric channel. So I guess what I'm trying to say is, for a given polynomial here, there are many polynomials that you could put up here where this relationship holds true. When you're building your lookup table, between S and E, only pick the E's with the least number of 1s for any given S. Okay, and then you have a maximum likelihood decoder. Okay, I think that'll do for today. We made it through without the power blinking out. Thank you to the power distribution powers that be. Get it? Okay, that's enough out of me. Have a good weekend. I'll catch you later.